look at several examples. The example we left off on was talking about finding indicated area. It was example number 2. And we had found, one more, sorry. We had found that this particular one had an area, where'd we go, where's my answer? Did I have to go on the inside to get it? I have it written down. Did we finish this one? I thought that we had. Had we?
Finished number 2, but not number 3.
Okay. Right. So we had gotten on this one, I believe we got pi over 12. Is that right? Oh, I know where I put it. There it is. All right, so we had pi over 12 as our final area for this particular one, right? All right, so last time when we were looking at this one, we determined the fact that we actually had to decide what the limits of integration were. And that involved, at least in part, setting things are equal to 0 and solving those particular pieces of information. Joel. So we're going to take a look then at this one, and we've gotten to the point where we set these equal to 0 to solve them. And I think it was after class, I don't think it was in the middle of the lesson itself, somebody came up to me and said, well, could we use from 7 pi over 12 to 11 pi over 12, which is a very reasonable question because those would be another part of the interval, that was between these particular values. The answer is actually no on this one because if you were to graph it, you would find out that the interval is going to be referencing here. It talks about the larger loop. And if you go from 7 pi over 12 to 11 pi over 12, you'll get the smaller loop. So this was one, and you gave me a graph on the homeworks that I just graded of one that looked something like this. Do you guys remember that particular graph? Well, the little loop on the inside is what this one would be referring to if you went from 7 pi over 12 to 11 pi over 12. So we're going to get the outer loop if we go from negative pi over 12 to 7 pi over 12. Did I say that right? Yeah. So that's how you're going to make that decision. And if you don't know which one to do, because we wouldn't have necessarily known that, you can graph that to decide which of those two sets of limits of integration are the ones that will actually give you the desired area. So you're just going to be aware as you're graphing which one of them actually gives you the outer loop versus the inner loop. Does that make sense? Okay. So for our limits of integration, we are going from negative pi over 12 to 7 pi over 12. We had this 1 plus 2 sine of 2 theta squared d theta when we left off last time. And when we got to this point on the last example, what did we have to do then? Tell me a few things that we're going to do. Somebody said it. I thought. Eventually, but we need to do something before we can use the trig properties. Yeah, we need to FOIL. So we're going to FOIL this out. When we do, we're going to get a sine squared. Once we have the sine squared, then we're going to use some properties of trig in order to be able to change that into something that we can integrate without any more complicated methods of integration. So let's distribute this out first. So this will give me 1 plus what? I multiply 1 plus 2 sine 2 theta times itself. What do I get? 1 plus what? And then what? Right. And I'm getting closer to where I need to not be. D theta. Okay, so the middle term comes from multiplying 1 times the 2 sine 2 theta and doing that twice because you have the inner multiplication and the outer multiplication when you do the binomial expansion. And then the 4 sine squared at the end comes from squaring that last term or multiplying it by itself. All right, so these pieces right here, these first two pieces, we can use integration techniques. Just it's not a big deal on those two. But the last one where it has 4 sine squared of 2 theta, that piece I actually need to change in order to be able to integrate it. But we have a power reducing formula, and it tells us what sine squared is equal to. So what is sine squared equal to?
1 minus cosine 2 theta over 2.
Right, so we're going to have 1/2 still out here in front. Integral from negative pi 12ths to 7 pi 12ths. I've got 1 plus 4 sine of 2 theta. And then I've got a 4 in front, so when I change the sine squared into something over 2, it'll change that into a 2. Agreed? And then I've got 1 minus, what was it that you told me?
Cosine 2 theta over 2.
Right. And it's cosine of 2 theta because in the formula we had theta originally. It doubles the angle. So ours will be 4 theta exactly. And then d theta. So we'll clean up just a touch before we actually integrate. We have the 1/2. We have the integral. I've got 1 at the beginning. I'm going to get right here a 2. So this is going to give me 3, right? 3 plus 4 sine of 2 theta. And then I've got minus 2 cosine of 4 theta, d theta. Does that look okay to everyone? The pieces of that all work out all right? Okay, give me just a second. Let me clean off this slide. Mm-hmm. It is over 2, but I reduced it. That's what I mentioned when I did it. I reduced it with the 4 in front. So that's why it turned into 2. So the 4 became a 2 because I was dividing by the 2. Yeah. All right, so this is what I'm working with now, and I'm trying to integrate. So let's take a look at this one. All right, so what's the integral of the 3?
3 theta.
Yep, 3 theta. How about the 4 sine of 2 theta?
Minus 2 cosine 2 theta.
Okay, so the 4 becomes a 2. Why? I think Caleb used that. Yeah, so the chain rule, I've got a 2 theta as my angle inside, so I'm going to have to divide by a 2 factor if I were to use like U substitution. It's the chain rule going on. So it is going to become a 2. Why is it becoming negative? Yeah, the derivative of sine is negative cosine. So this is negative, and then I've got the cosine of 2 theta. Very good. All right, how about the 2 cosine 4 theta? That will stay positive, or stay negative, right? It won't change to positive. The sign won't change. The antiderivative of cosine is sine, and the angle doesn't change. What's going to happen in front? I'm going to get 1/2 because I have to take the 2 that's already there divided by the 4 that's on the inside with theta. So this gives me a 1/2 here in front. All right, and we're evaluating this at pi, we're at 7 pi over 12 and negative pi over 12. Now some of you are doing some very interesting things on things that I graded, and they don't include unit circle. So if you're using your calculator as a reference, that's fine, but you need to be able to recognize that if something turns, is coming from the unit circle, an exact answer is what's appropriate. So on these, we're going to have some pieces of this. So this is 3 times 7 pi over 12 minus 2 times the cosine of what angle will this actually be? It will. It'll be 7 pi over 6, which is a unit circle value. And then I've got minus 1/2. The sine of, and what will this angle be? 7 pi over what? What was it? 3? Mm-hmm. And 7 pi over 3 would actually be equivalent to what? I mean, what location in terms of its angle? Do you know? It's pi over 3. So this is actually 2 and 2 plus pi over 3. So it's actually the same location as pi over 3, which might be helpful when you're actually calculating. All right, and then we're going to take all of this, and we're going to subtract what we get when we plug in negative pi over 12. So this is 3 times negative pi over 12 minus 2 times the cosine of, now we've got negative pi over 6, minus 1/2 times the sine of negative pi over 3. Did I get all those in there correctly? And all of that has the 1/2 in front of it. everything there except for the 3 times the different values with the pies in them are unit circle issues. We would use our unit circle to calculate those particular quantities. So right now I've got the 1/2. I'm going to go ahead and combine the 2 pieces that I do have that are the same. These 2 can be combined. So I've got 7 pi over 4, and then I've got plus pi over 4. Does that look right? So that actually ends up being what? 2 pi. All right, so we'll simplify that in the next step, but that will be 2 pi. All right, let's work with some of these values here. What is the cosine of 7 pi over 6? Yes, so you're going to end up getting square root of 3 over 2 times 2. Is it positive or is it negative? Did you catch that one? What quadrant are we in? Do you remember? Yeah, if you're doing 7 pi over 6, you're in the 3rd quadrant, right? So the cosine and the sine value would actually be negative in that quadrant. So this would just be negative. So I've got the negative right here as a part of the 2, and I've got another negative, so I'm going to get a positive 2 times the square root of 3 over 2. Or if you prefer, you can write it out as negative 2 times the negative square root of 3 over 2, and it'll be positive in a minute. We'll leave it that way just for fun. Then I've got the negative 1/2. What is the sine of, in essence, pi over 3? That is square root of 3 over 2. So we're definitely going to be able to combine some of these square root of 3 over 2s because I've got a couple of them now. All right, down here, I've got this negative out here in front that's going to change this sign to being positive. So I've got positive 2. What is the cosine of negative pi over 6? What quadrant am I in? Well, I'm in quadrant 4. So is the cosine positive or negative? It's positive. And what's the value for cosine at that particular location? It's radical 3 over 2 again. I'm getting a lot of those. And then the same thing's going to happen with my sign on this one. I've got this negative in front of my 1/2, but I've got a negative on the outside, so it's going to be a positive 1/2. Negative pi over 3 is also in quadrant 4. So what's the sine value there? One's actually negative. And what is the sine value at pi over 3? Square root of 3 over 2. All right. So you guys told me just a moment ago that this is 2 pi with the first 2 pieces, right? So I've taken care of these 2. I'm going to have a positive next, and my 2's are going to cancel, right? So I've got the 2 and this dividing by 2, so this is positive square root of 3. The next piece I've got is negative square root of 3 over 4. And then I've got this 2's canceling out, so that's positive square root of 3. And then I've got a positive, a negative, because it's being multiplied by the negative underneath, square root of 3 over 4. So in essence here I've got 1 minus 1/4 plus 1 minus 1/4, and then it's times the square root of 3. That's what I've got to deal with. So what do I get when I take 1 minus 1/4 and I add another 1 and I add minus 1/4? This is 2 minus 1/2, which would be 3/2. Did everybody get that? So this is 3/2 times the square root of 3, because they all had a square root of 3 in them. So I've got 1/2, 2 pi, plus 3 halves square root of 3, or you can write 3 square root of 3 over 2, of course. And we'll distribute 3 by the 1/2, so this becomes pi plus 3 square root of 3 over 4. And that would be the value of the area of that larger loop of this particular polar coordinate graph. There's nothing in there after we got the problem set up that you couldn't have done in Calc 2. Right? It's all Calc 2. Now, that may have been a while. I know it has been a while for some of you. But now's the time to brush up on it. And for sure, some of you need to brush up on your trig, and I'm getting blank stares all over the place when I'm talking about unit circle. So some of you need to get out of unit circle again. And we talked about that last time or the time before, so please make sure that you've done that. All right, one more piece of information in this section, or one example. Talking about arc length. So when we talked about arc length back in the parametric section, we defined the arc length to be s equals the integral from a to b of the derivative of x with respect to theta squared, the derivative of y with respect to theta squared, and then the square root of all that d theta. That's how we cleaned it up and defined it to be. So we're going to do the same thing that we did last time, where we use this information to create the same thing for our polar coordinate system. So our r value is f of theta, and then x is r cosine theta. So if we replace the r with f of theta, we get that x is equal to f of theta cosine theta. And we can do the same thing for y. Y is r sine theta, and if r is f of theta, we get that y is equal to f of theta sine theta. So if we do that, what that means is that we can take this curve, and we're going to do some simplifying. So I want to show you where this is coming from. I just want to look at the part of the things underneath here squared. X prime of theta squared plus y prime of theta squared. Okay, and then we recognize that when we get back to the formula, this is going to be all underneath a square root with an integral on the outside and so forth. But we're just going to clean this up. So taking a look at how we've defined things, this is now actually equal to f of theta cosine of theta squared plus f of theta sine of theta squared. Right? We're going to square that now. Okay? Oh, I'm sorry. We need to take our derivatives first. We haven't done that yet, have we? We did those from last time, though. Let's go and pull those in here. Let me do notationally. Let me change something. We're supposed to do... You know what? Let me just erase the piece that I've done so far. I'm sorry. I got ahead of myself. Last time we found the derivatives. They were back on maybe the first page of your notes. Yeah? So let's use the derivatives we found from last time, and we'll put those in. All right, so we had f of theta, for x prime, we had f of theta cosine of theta. I'll write the note, I'm sorry, I'll put it in the order you guys gave it to me because I believe you had it backwards of how I wrote mine down. F prime of theta sine theta plus f of theta cosine of theta squared. And then for y, we had f prime of theta cosine of theta plus f of theta cosine of theta. Squared. I'm running off the side of my page. Hopefully you're not. It's better. Okay, so that was from last time, those particular pieces. Now when we square it, it'll be more fun, because that last one just wouldn't have been any fun when we squared it, would it? No, it wouldn't have been any fun. So we're going to square this one, and we're going to get lots of pieces, right? Because when we square, we're going to have to actually FOIL each piece of it together. So on the first piece... Oh, did I? Did I write them in there backwards? You're right, I did. Yeah, you're right. I wrote them in there backwards, but you're right, it doesn't matter since it's plus. Okay. Good to know. Sorry about that. All right, so we're going to square each of these, right? So on the first one, I'm going to get f prime of theta squared sine squared of theta. That good? I know f prime of theta squared looks funny like that, but it'll all simplify out here in a little bit and it'll be fine. All right, when I FOIL this and I multiply the two terms, the f prime of theta sine theta and the f of theta cosine theta together, when I multiply those two together, I'm just going to get two of them. So I'm going to get 2 f prime of theta and f of theta, and then I have sine of theta and cosine of theta. And then I'm going to square the last term, so I'm going to get f of theta quantity squared, and I'm going to get cosine squared of theta. All of that is multiplying the first piece right here out. That's all I did. And we're going to add that to the next piece being FOILed or multiplied out as well. So I'm going to have f prime of theta quantity squared times cosine squared of theta. And then I have plus, I feel like I'm messing a sign. Didn't one of these have a negative sign in it? Yep. This one, right? Has a negative here? Okay. All right, good, because then I'm going to have a negative. Oops, we'll fix it. So I have negative, and I'll double the inside terms. This is 2 f prime of theta, f of theta, sine of theta, cosine of theta. And then I've got plus f of theta squared, sine squared of theta. I'm not going to write any of these pretty much again because many of them are going to clean up. So what's the first obvious cleanup? Yeah, these two in the middle are the exact same thing but opposite signs, so those add to 0. Now, each of the other pieces, although the reason I'm writing it this way is because I don't have room on my screen, it's actually really nice to have it written this way because you can see the pieces that kind of go together because they're sort of stacked on top of each other. So the first two both say f prime of theta squared, and then one of them is times sine squared and one of them is times cosine squared. So when we add those two pieces together, we can factor the f prime squared out, and then I've got sine squared plus cosine squared, which equals 1. So what really ends up happening is that we get f, well, let me use black, f prime of theta squared, and that's all we get left. We don't get the other pieces of it at all because sine squared plus cosine squared is 1. And the same thing happens at the end of this, right? I've got f of theta squared in both of them, and one of them is cosine squared and one of them is sine squared. When we add them together and we factor out the f squared, right, we are going to end up with the sine squared plus cosine squared, which is 1. So we only end up with f of theta quantity squared. I think I intended to do all that work on that slide, but that's okay. So the result of all of that is that that piece is what's going to go underneath this radical right here in place of the x prime of theta squared and the y prime of, plus the y prime of theta squared. Is I'm going to have the derivative squared and the original function squared. So I end up getting, I'll move it back up here, s equals the integral from a to b of the square root of f prime of theta squared plus f of theta squared d theta. So that's where the formula is coming from that we are going to be using. It's coming from that parametric system with a substitution and some nice cleaning up of things. All right, so we're going to do this particular problem. This r is f of theta. So I already know f of theta. I'm given that. I do need to find f prime of theta. So what is the derivative of 2 plus 3 sine 3 theta? Nine cosine of 3 theta. Okay, everybody good so far? So if I'm going to find the arc length, I need to find my arc length. This particular graph, let me just pause here. We do need to know our limits of integration. We don't have that yet. I will just say that if we take a look at each of these and set this equal to 0, this is sine of 3 theta. Do you remember what that graph looked like without graphing it? You've done it a couple of times. What's that? It does start at 0, that's correct. But do you remember what the graph looked like in terms of its overall picture when you graph enough of it to see the whole thing? It looks like flower, exactly. Do you remember with how many petals, Nathan? This one happens to have 3. Anytime it's an odd number inside the angle, that's how many flowers, petals it has. If it was even, it actually has double that number of petals. So this one is a flower with 3 petals. And it takes a full rotation from 0 to 2 pi, to get all 3 petals. So the correct value actually is that it's going to go from 0 to 2 pi. And I'm using the fact that we've already graphed this before to make that assumption. And so if you weren't working with something you've graphed before, you could graph it to see that piece of it. All right, and then I just talked about the 3 sine 3 theta part of it. The 2 plus part of it's going to end up giving you a different graph. Obviously, you're not going to have a graph that's going to look like a flower any longer because of that piece of it, but it doesn't change the limits of integration any. It's still going to be from 0 to 2 pi. I want to say 3 pi. That 3 in there keeps making me say the wrong thing. All right, so we're going to be doing the square root of each of these functions, so 2 plus 3 sine of 3 theta squared, and the derivative, which was 9 cosine of 3 theta squared d theta. And I guess I actually put these in backwards of the way I wrote my formula before as well, because my formula before I wrote the derivative first, but because it's addition, it doesn't matter. Let me give you a little bit of a heads up. The ones that we're going to be working with, for the most part, are not going to clean up enough underneath the radical for us to actually be able to solve this by hand. But until we get to the point where we recognize that fact from what we're working with, we are going to try and clean it up as best we can. Okay, so we're going to square this out. All right, so what do I get when I square out 2 plus 3 sine 3 theta?
12 sine squared 3 plus.
It'll be sine 3 theta first, not squared.
Yes.
Right? Okay, good. And then what's next, Jordan?
9 sine squared 3.
Good. The other piece is easier to square because it doesn't have any addition in it, so it's just going to be 81 cosine squared of 3 theta. There's a d theta there on the end. It's kind of looking funny, but it's there. I can't combine these right now because they don't have the same number in front, so I can't just pull out the sine squared and the cosine squared and say they equal 1. That'd be great. But we don't have that fact on this particular one. If I hadn't had a coefficient in front of that theta, I actually would have been able to do that on this particular problem. But I do in the problem, so I can't deal with it that way. However, I can change one of them into the other one. My suggestion is to change the cosine into something with sine in it, because I've got something with sine in it also in the problem already. Does that make sense? So we're going to use those not power-reducing angles, but the Pythagorean theorem to change that expression. So this is the integral from 0 to 2 pi. I've got the 4 plus the 12 sine of 3 theta. And I've already got the 9 sine squared of 3 theta. And we're going to add to this 81 times what? I already gave you 1 minus, right? Sine squared of 3 theta. D theta. We'll distribute the 81, which will then combine with the coefficient at the very beginning, or the constant at the very beginning. And then when I distribute the 81 to the sine squared, I'm going to get negative 81 of those plus the 9 that I had originally. All right, so taking a look at what I've got, I have 4 at the beginning plus 81 more, which is 85. And then I have plus 12 sine 3 theta. And then I've got 9 minus 81. It's going to be negative something. Negative what? 72 sine squared of 3 theta. Now let's just pause for a moment and think about this. If I didn't have the square root, we could use a power-reducing formula on the sine squared, and we could integrate this. Agreed? But the only way I can deal with this with a square root with nothing outside of it is if what's underneath there factors into a perfect square. And this just doesn't. I can know this isn't going to factor into a perfect square by this sign alone. If I've got a negative on one of the squares, it can't factor into a perfect square. Because with a perfect square trinomial, they're both positive on the ends. So this one will not factor, which means I can't go any further into attempting to clean this up. Okay? So we didn't clean up very much, agreed? This wasn't horrendous or anything like that. Once I get to the point where I recognize I have to be able to factor this and I can't, then I'm done, and then you're going to use your calculator to solve this. So I want you to take your calculator and turn it into into the regular mode, the standard function mode. I actually tried this in radian mode and I couldn't get it to work, so I'm probably missing some sort of piece of what I'm supposed to be doing. You should be able to do this in radian mode and actually integrate this, but I was not being successful. I know it will work in function mode though. If, as you're entering this in function mode, you can enter this into y equals. So you can write down y1 equals. You can put the square root, of course, in, which will just look like that. You need a parenthesis, or it probably will put one in for you. You've got your 85 plus 12 sine. It will force the 3 to be in parentheses, and the variable you'll be using is x. And then minus 72, you'll need a parenthesis to start this. Sine of 3 theta, where it'll force you to another parenthesis. Make sure you close that parenthesis, then square it, and then you close your parenthesis for the whole thing. So this is what's going to go into y1. And then you can choose Math 9. You can do a graph if you want to do it from the graph and do the integration. Doesn't matter to me. But you're going to integrate this from 0 to 2 pi, and you're going to get, of course, an approximation. And we'll go with 2 decimals because that's what we've typically gone with in class. So what happens when we integrate this and we approximate to 2 decimals? Did anybody get an answer at this point? I agree. 41.54. Hannah, is that what you got on yours? Did yours, is it still calculated? It takes it a while, doesn't it?
That's what I got.
That's what you have as well. Okay.
I left mine in folder,
Did you leave yours in Polar?
but I have a CIA for.
Do you have a math type one where it has it in the pretty type?
Yeah.
Okay. Yeah, I think that there's a notation thing with the older version, the older operating system, that I'm not knowing how to detail it out quite right. But good, good, good. All right, so we get 41.54 for our area. I'm sorry, or not our area, our arc length. That's what we were looking at. Any questions on that? All right.